All right, so to start talking about Simpson's rule, I've constructed an example of the trapezoidal rule off tape because I couldn't talk and construct at the same time. You can see that the trapezoidal rule involves taking intervals or subintervals, excuse me, of the exact same width. In this case, we have two subintervals just for the example, but the width of one and the width of two have to be the same. So each partition has the same width. And then finding the point of intersection to the curve, the trapezoid rule says to connect those, and I would get some approximation of the area under the curve. Now you can see clearly that in this region, I've approximated the area for this partition, but this is an over approximation here. So Simpson's rule takes it one step farther, and let's see if I can sketch this in, hit all my targets, that if we're able to make the same approximation, only this time with a quadratic or a second degree polynomial being at the top rather than the trapezoid at the top or intersecting with the curve, then I get that much closer to the actual area under the curve. And let me sketch that out a little bit. The part I eliminate, or the error that gets eliminated, is out here. So this is extra area that the trapezoid rule estimates in, but Simpson's rule does not. So I get that much closer to the actual area under the curve. And that would be true at each interval. This would produce a parabola in the opposite direction. So Simpson's rule, luckily, you don't have to, just like with the trapezoid rule, you don't actually have to sketch out the curve. This was just to make the point. It's a formula that helps us set up on an interval some chosen number of subintervals and then gives us a way to calculate the parabolas on each interval. Now, it's important when we talk about Simpson's rule to know that n in this case has to be even. Has to be an even number. So the trapezoid rule, you can have subintervals that are an odd number of subintervals, but for the Simpsons rule, you have to have an even number of subintervals. But still, each interval has to be equal in length. So for Simpson's rule, we're still looking at interval widths that are equal. All right, so that's as far as I want to take the visual or the understanding visually part of this lesson. We want to treat Simpson's rule pretty much like a pluggy-chuggy formula. So we're going to plug our values in and then we'll just chug until we get our final answer. So we're saying that the antiderivative or the integral of a function is approximately equal to b minus a divided by 3n. Notice that's slightly different than the trapezoidal rule. And then each of our, how do I want to say this? Each of our top values, so the curve that we'll be using for the estimation, is found by plugging in the f of xo. This looks very similar to what we did before, plus 4 times the f of x1 plus 2 times the f of x2 plus 4 times f of x3 plus, I run out of room, so I'm going to move it down here, plus 2 times the f of xn minus 2 plus 4 times the f of xn minus 1 plus 1 time the f of xn. So it's very similar to Simpson's rule in the fact that the first and last terms have no coefficient multiplied to them, or no multiplier for each term, but each term in between has a pattern of 4, 2, 4, 2, 4, 2, 4, 2 until you get to the end. So granted, all of that is very tedious to listen to and to write, but let's see how it works in a real example. I want to estimate the area under the curve of 1 over x dx on the interval from 1 to 3. Now, the good news is I don't have to draw this or even try to calculate the subintervals. I do sort of have to visualize what must be happening in this case. And so I have to come up with some subintervals that make sense. I'm going to use n equals 4. And so now I can just pluggy-chuggy my way through this whole process. The first step is to find my delta x values. And there's nothing new here. This is b minus a divided by however many intervals I want, n intervals. So in this case, I'm looking at 3 minus 1 divided by 4, which is 2 over 4, which is 1/2. So I know that each interval width is going to be 1/2. I do have to find the location of them. I don't have to do any calculations toward understanding the area of each partition, but I do have to find the location of each of the edges of the partition, starting with the first one to the edge that falls between the first and second partition, and then the third and fourth, and so on until I run out. So I know that I'm going to have an XO value, or my first value has to be on the left-hand edge or on the lower edge of the entire area. So that would be x sub O equals 1. And then I have x sub 1 equals 1 plus 1/2, which is 3/2. And x sub 2 would be 2, because we're looking at 3/2 plus 1/2, so that's 2. And then the third value, or the third height, would be x sub 3, which is 2 plus 1/2, so that's 5/2. And then x sub 4 is 3. 5/2 plus 1/2 is 3. And so for n equals 4, these are the 5 values I need to find, and that makes sense. If I divide something into 4 partitions, if you look at the space between your fingers and your fingers, not your thumb, and you notice that they're 1, 2, 3, oh, I have to use my thumb. If you look at the space on your hand between your thumb and first finger, your ring finger to your middle finger, and so on, you can see I have 1, 2, 3, 4 spaces, but 5 fingers to contain that on both sides and create the subintervals. So for n equals 4, I'm going to have 5 values. Probably didn't have to take you through that journey of discovery on your hand, but at least I hope you found something interesting to look at. Let's get back to the math of it all, the calculus. So let's set this up. We're going to use the formula for Simpson's rule now. So the integral on the interval between 1 and 3 of 1 over x dx can be approximated by 3 minus 1, still using b minus a, over 3 times n equals 4 times, well, 1 over 1 is 1, plus 4, remember we have to constantly be remembering to use our multiplied coefficients in the front. Regardless of what the function gives us, we're going to multiply in an extra value. So 4 times 1 over 3/2, which is just 2/3, taking the reciprocal, plus this time 2 times 1 over 2 is 1/2, plus this time 4 times 1 over 5/2, which is 2/5, plus, and this is our last term, so we won't be multiplying anything in front, and I'm just looking at 1 divided by 3. Okay, so 3 minus 1 is 2, divided by 3 times 4 is 12, and 1 plus 8/3 plus 1, 2 times 1/2 is 1, plus 4 times 2 is 8/5 this time, plus 1/3. Well, this is 2 plus, I'm hoping I can reduce without having to do another common denominator. Well, 3 and 5 have a common denominator of 15. So 3 times 8, or 3 times 5 is 15, 8 times 5 is 40, plus 5 times 3 is 15, 8 times 3 is 24, and 3 times 5, so 1 times 5 plus 5. And these still have to be divided by 15. So what is that? That's, whoops, I forgot to write the 1/6 here. So 1/6 times 2 plus 40, 64, 69. Well, I can at least do some reducing with 69 and 15 before I start combining. So 69 divides by 3, leaving 23, and 15 divides by 3, leaving a 5. So I have 1/6. All right, I'm not going to be able to get rid of that denominator, but I do have just a 5 in this denominator, so finding a common denominator inside means 5 times 2 is 10 plus 23 over 5, which equals 33 over 6 times 5. Now, I didn't combine the 6 times 5 and write 30 because it's just as easy if I have a common factor to go ahead and reduce from here. 33 divided by 3 is 11, and 6 divided by 3 is 2, and so I end up with 11 tenths, or if I want to use a decimal, I can write 1.1. All right, I think we have time to do another Simpsons rule, if we make it quick. So, example, we want to estimate the area under the curve with Simpsons rule, the interval, or the integral 0 to 2 on the interval from 0 to 2. I think it's getting late. I'm having a hard time forming my words. X cubed minus 1 dx. And we're being told that we want to use 4 subintervals, so n equals 4. All right, so let's put this together in our formula. First thing we need is a delta x, and delta x is b minus a, so 2 minus 0 over n, 4. So again, this is going to be 1/2, so it should be easy for me to put together my subintervals. 0, so my x sub o equals 0. Then my next vertical, or the next boundary on my partition, will be at x equals 0 plus 1/2 is 1/2. X sub 2 is going to be at 1. 1/2 plus 1/2 is 1. X sub 3 is going to be at 3/2. 1 plus 1/2 is 3/2. X sub 4, 3/2 plus 1/2 equals 2. And so there are my subintervals. So now I'm ready to just plug everything in and get going. And I'm sort of realizing the error of my ways. I wrote all of this stuff here. I wish I hadn't. I wish I had written the n equals 4 here and calculated across, because then I'd be able to just put an equal sign and start going, but I can't. Since I'm talking about the algebraic process, if I put a bunch of stuff in between the initial problem, I have to rewrite the initial problem. So from 0 to 2, x cubed minus 1 dx. Now, sometimes you can get away without doing that. It just depends on your grader. If you have a bunch of work in here and you're not very neat, the person gets lost in this area and they're done grading. If you're taking the AP test, that could cost you a lot. If you're just taking my test, maybe not so much. It all depends. But anyway, you want to be as careful as you can. And so what we're going to do is approximate. So I want squiggly equal signs. So I want b minus a. So that's 2 minus 0 over 3 times 4. Right? So that's 3 times whatever n is. And now I need what's inside. So remember the first one, the f of 0, I'm not going to put any number multiplied out front. So the f of 0 in this case is negative 1. Right? So if I take x cubed, here I am, 0 minus 1 equals negative 1, plus, now I'm going to start the 4, 2, 4, 2 pattern until I get to the end. So 4 times the f of x2, so 1/2 cubed is, 1/2 cubed is 1/8 minus 1, negative 7/8 plus 2, 4, 2, 4, 2 pattern, times 1 cubed is 1 minus 1 equals 0. Oh, we love those zeros in these kinds of calculations because everything disappears, or at least that part does. Plus 4, 2, 4 times 3/2 cubed 27/8 minus 1, which is 8/8, is 19/8. Plus, now this is my last one, so I'm not going to put a multiplier in, not a 4 or a 2. So my last one is just 2 cubed is 8 minus 1 equals 7. And so let's go ahead and reduce this or simplify it. So 2 minus 0, 2 divided by 12 is 1/6 again, of course. If n is that, yeah, 1/6 again. And then negative 1, this is a 0. Negative 1 plus 7 is a positive 6 plus, oh, that's going to be a negative, minus, well, 4 reduces with 8, leaving a 2, so that's minus 7/2, plus 4 reduces with 8 again, leaving a 2, so that's 19/2. And I've already used the 7 to make the 6. So this is approximately equal to 1/6 times, and I think I'm going to go ahead and make a common denominator, 12 minus 7 plus 19 all over 2. So I get 1/12 times 12, take away 7, 5, plus 19, 24. Oh, that's convenient. 24 divided by 12 just equals 2. So that's it. Simpson's rule, just like the trapezoidal rule, is a formula, pluggy-chuggy math for finding the area, or estimating the area under the curve.